today is our last lecture in this semester. So, and I will first of all finish the material, and then maybe I will tell you about something more interesting. Okay. Let me prove a couple of theorems which I told you already about, but I need to prove them. That if lambda 1, lambda 2, lambda k are distinct eigenvalues, corresponding to eigenvectors v1, v2, vk, then these vectors, these eigenvectors, are linearly independent. Okay, I will prove it for a general case of the linear transformation, but of course you can do the same using matrices and so on with respect to some basis, matrix representation of this linear transform with respect to some basis. Okay, let us suppose that only R, which is less than K, of vectors are linearly independent. Okay, what it means? It means that let me suppose that it's first. So 1, 2 are vectors linearly independent, and R plus 1, R plus 2, and so on till K linearly dependent. So if I add any of these, it's better to write it not like that. So independent, yeah. So these first R vectors are linearly independent, and if I add any of these vectors already, so I'm getting linearly dependent collection of vectors. Okay. What I will try to prove, I will try to prove that R has to be equal to K. Okay, let us consider linear combination of R plus 1 vectors. Because if I include these R plus 1 vector, already this has to be linearly dependent combination, then this linear combination has to be non-trivial, because these are R plus 1 vectors already linearly dependent, right? Because we said that only first R vectors are linearly independent. Okay, and also it means that these cannot be equal to 0. Why? Because if it's equal to 0, then we are saying that these already has to form non-trivial linear combination, right? When not all C's are equal to 0, but it contradicts the fact that these vectors are linearly independent. Okay, then I will do the following. So let me apply. So applying here my H linear transformation, and then I'm getting once again. So what is? So I have that Vi, right, equals to lambda I Vi, right? So it's a definition of the eigenvector, right? So I'm getting C1 lambda 1 V1 plus C2. Yeah, because it's linear, so I can apply it term by term, right? C2 lambda 2 V2 plus and so on, plus CR lambda R VR. Okay. Let me write it like that. Plus CR plus 1 lambda R plus 1 VR plus 1 equals to 0, right? Because linear transformation applied to zero vector always gives a zero vector. Okay, now I also let me multiply. Oops, not here. Let me multiply these by lambda R plus 1. So I will get C1 lambda R plus 1 V1 plus C2 lambda R plus 1 V2 plus CR lambda R plus 1 VR plus CR plus 1 lambda R plus 1 VR plus 1. So is it clear how I got this and that? Any questions?
Yeah, what's the H? I missed what the H was.
H is the linear transformation for which we have these eigenvectors and eigenvalues. Okay.
Thanks.
Mm-hmm. Okay. This is how I defined eigenvectors and eigenvalues in general, right? So you can also define it for the matrix, but you can do this for linear transformation in general. Okay, now let me subtract second expression from the first one. Then I'm getting C1 lambda 1 minus lambda R plus 1 V1 plus C2 lambda 2 minus lambda R plus 1 V2 plus and so on plus CR lambda R minus lambda R plus 1 VR, and these will cancel, right? So this has to be equal to 0. So pay attention that because we started from the fact that eigenvalues are distinct, right? Then this is not equal to 0, this is not equal to 0, and so on, and all these are not equal to 0 because eigenvalues are distinct. But then it means that the only possibility for this to be equal to 0 when all these are equal to 0, right? Because these vectors are linearly independent. We said that suppose that only our first vectors are linearly independent, right? But then it means immediately that all these has to be 0, 0, 0, right? Okay, great. But if all first R coefficients are zeros, then from here it follows that CR plus 1, pay attention, which is not equal to 0, right? VR plus 1 equals to 0 vector. But we know that eigenvector cannot be zero vector. It's by definition non-zero vector. So then we got a contradiction. Correspondingly, R cannot be less than K. So which means R is exactly equal to K. So which means that if we have K distinct eigenvalues and corresponding them eigenvectors, these eigenvectors are linearly independent. Pay attention that you can have repeating eigenvalues. So in other words, eigenvalues which are not distinct, but still you can, or maybe, I mean, you might, let's say like that, you might get linearly independent eigenvectors. So for repeating eigenvalues, sometimes you get still, for example, you get the eigenvalue which repeats twice, right? So, and you can still get, for example, two linearly independent eigenvectors for that. But there are situations when you will not get it. And then this is when you need to do this. So you will not have enough linearly independent eigenvectors, and this is when you need to do so-called bring it to the Jordan canonical form. But it's different story. So if you want to study this, please take 471 or 462, I believe. So we study this usually in the graduate course for unit differential equations. Okay. But now, based on that, pay attention. So once again, the fact that you do not have n distinct eigenvalues doesn't mean that you will not have n distinct eigenvectors, okay? Because even in the case of repeating eigenvalues, you might get still enough eigenvectors, linearly independent eigenvectors. Okay, now, theorem. An n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. So the diagonalizable means that you can find non-singular matrix X such that this will be diagonal matrix. So if you have a look at this, you see that essentially what it means. You can consider this matrix X, every column of this matrix, you can consider it as, because they are all n by n, n by n, n by n, n by n, right? Every column of this matrix X, you can consider as a vector, column vector. And then this is nothing else that you are switching into the basis of these column vectors of the matrix X. And in the basis of these column vectors, your matrix A, the representation of your linear transformation, become a diagonal matrix. So if you will have a look at this form and you remember what you get essentially when you change the basis, so this is exactly changing the basis to correspondingly the columns of this matrix X. Okay. Now, statement is if and only if A has n linearly independent eigenvectors. So, which means that if you have n linearly independent, n distinct eigenvalues, right, for the n by n matrix, then immediately you know that according to the previous theorem, you have n linearly independent eigenvectors, and then your matrix is diagonalizable. But as I told you, even if you don't have enough distinct eigenvalues, there can be situation when your matrix is still diagonalizable, because you will be able to find enough linearly independent eigenvectors. Okay, so let us here I will use the following proof that let us suppose that we have v1, or let's say x1, x1, x2, and so on, xn, linearly independent eigenvectors, and lambda 1, lambda 2, lambda n corresponding eigenvalues. Not necessarily distinct. So they can be repeating, doesn't matter. The main fact is that I have n linearly independent eigenvectors, sorry. Okay, then if I consider matrix X, which consists of x1, x2, xn, so corresponding vectors, column vectors as columns of this matrix, then if I apply my matrix A to the matrix X, which is, by the way, non-singular, right? Is it clear? Is it clear or not that this matrix has to be non-singular?
It's clear.
Okay, because all columns are linearly independent, right? Okay, so if I apply this matrix A, so what I will get? I will get essentially AX1. So how I multiply matrix on the matrix? So I multiply matrix on every column, right? And then I'm getting that this is lambda 1. X1, lambda n, xn. So this is we already had. So, and this is the same as matrix X multiplied on the following matrix: lambda 1, lambda 2, lambda n, diagonal matrix D or L, lambda capital. Let me call it lambda capital. Pay attention that order of the eigenvalues has to be the same as order of the vectors in the matrix X. But then from here, it immediately follows that if I will multiply by X inverse from the left, I get exactly this representation. And so I have proven it in one direction. Sorry. But then if matrix is diagonalizable, then from here immediately it follows that there exists matrix X such that AX equals to XD, right? So I just multiplied this expression by the X, matrix X from the left. But then from here, I'm getting that AX1, the first column, equals to D11 X1. AX2 equals to D22 X2, diagonal elements, right? And so on. AXN equals to DNN XN. But this means that what I've got that corresponding columns will be nothing else but eigenvectors of a matrix A with corresponding eigenvalues, which are diagonal elements of D, right? D is D11, D22, DNN, and zeros everywhere else. Okay, and also because matrix X has to be non-singular, because of this, all x's are linearly independent, right? So all vectors x1, x2, and so on till xn has to be linearly independent. Now I have proven theorem in both ways. Okay, that's it. Now I just want to tell you why it's useful to find the diagonalization of the matrix. First of all, let me suppose that I want to compute a to 100th power, right? Yeah, by the way, so you see, this is diagonalization, right? We got D. From the other point of view, you can let us multiply by x from the left and by x inverse from the right. And then this will be nothing else but A, right? Okay, if I want to compute A to the 100th power, really, let me say nth power. Then how can I do this? I just means that I need to multiply A n times, right? Okay, what it means? It means that I can write this as like that, right? But have a look. Here, this is identity matrix, right? Here, there also will be identity matrix. And here will also be identity matrix because it will be x inverse multiplied on x. So result will be just this. But in order to compute nth power of diagonal matrix, so when you will be multiplying diagonal matrix on itself, you can see that what happens. You just multiply D11 on itself, D22 on itself, DNN on itself. So yeah, really, let me use K because N we use already for the size of the matrix. Will be nothing else but D11 to the kth power, D22 to the kth power, and so on, DNN to the kth power, just diagonal matrix. So this you can do easily, right? And all you need to do after that, multiply by corresponding matrices. Is it clear or not? So you use way less operations. So when you need to multiply matrix on a matrix, you need to use how many operations if it's n by n matrix. For every term, you need to use at least, if you even computing only multiplications, not additions, you need to use n operation for every term, right? But altogether, there are n by n entries. So it means that altogether you need to use n cube multiplications, right? Here, you just compute the corresponding powers, and then multiply by 2 matrices. That's it. Is it clear or not?
It's clear.
Yeah. Also, another I told you already about application of the diagonalization before. How to solve systems of ordinary differential equations. So if you have this differential equation, then if you can find that this if you can find diagonalization of the matrix, so then have a look. So for example, yes, A equals to, or yeah, A x d, or let me call it lambda x inverse, right? So let me put this here. So I can write that this is x prime equals to x lambda x inverse x. And let me, for example, multiply from the left by x. So let me call y to be this, because it's just a vector, right? Then this you can write like that. So it's y prime equals to lambda, and here is y. So, but this is diagonal. So how it will look like? Y1 prime equals to lambda 1, y1, y2 prime equals to lambda 2, y2, and so on. Yn prime equals to lambda n, yn. So solution of that is nothing else but y1 is a function of time at initial moment of time e lambda 1 t, y2, y1, y2 at the initial moment of time e lambda 2t, yn initial moment of time e lambda nt. So as a result, you know immediately solution as y, right? How to get x? All you need to do, you need to multiply by the matrix of eigenvectors this y. That's it. So essentially x as a function of time is nothing else but matrix of eigenvectors multiplied on y. This is how you solve systems of linear equations. If you can diagonalize the matrix, if you cannot, so then you can prove that you can bring it to almost diagonal form, so-called Jordan canonical form, and then it's a little bit harder, just a little bit. Okay, this is where you apply it. Now let me tell you a little bit how to simplify the situation of computing the eigenvalues, and so computing this. Let me remind you that for a matrix A, you use this, right? So in one of your homeworks, you have proven that this is for n by n matrix. It's a polynomial of degree at most n, right? So in other words, so when you multiply it, so you will get some lambda to the power n on some coefficient plus lambda to the power n minus 1 on some coefficient and so on, right? So, and you're getting that this is polynomial of degree n, but polynomial of degree n, according to the fundamental theorem of algebra, can have at most n roots, right? Really, fundamental theorem of algebra tells you that if you take into account complex roots, then it's exactly n roots taken into account multiplicities, which means repeating roots. Okay, but now let me tell you a little bit so about this thing. So it's a11 minus lambda, a12, a13, a1n, a21, a22 minus lambda, a23, a2n, a31, a32, a33 minus lambda, and so on, a3n, an1, an2, an3, ann minus lambda. So we need to compute this determinant, right? So first of all, let us have a look at it and say that, okay, this is the polynomial, right? Pay attention that all lambdas here, they are coming with negative signs, right? So as a result, how you can factor it out? You can factor it out in the following way. Okay, you can factor it out in the following way. Lambda 1 minus lambda, lambda 2 minus lambda, lambda n minus lambda. This is equal to 0, right? So why? Because if you will compute this determinant, so you will see that the first term, because it will be multiplication. So what will be, okay, let me call this polynomial of degree n on lambda. So what we can tell about this polynomial of degree n on lambda? So we can say the following, that first of all, it will have, so when you are multiplying these brackets, right? What can you tell me about coefficient in front of the lambda n? Yeah, by the way, this polynomial is called characteristic polynomial. Okay, when I'm multiplying all the brackets, how to get lambda to the power n? I need to multiply all these things on each other, right? N brackets, I need to multiply n times on each other. And then here I will get -1 to the power n, right? Plus, okay, how to get coefficient at lambda n minus 1? So in order to produce lambda n minus 1, so what I need to do? I need to multiply n minus 1 times these -1s, -1 lambdas. So, okay, let me erase it. Negative lambda to the power n minus 1. But then here I will have just lambda 1 for if I use this bracket in order to produce, so all others are negative lambda to the power n minus 1, and here I use lambda 1. Then I can do the same using lambda 2 from this bracket and negative lambdas from all others, and so on, lambda n, and so on. Okay. Now, let us see what I will get if I will consider if I take this, right? Substitute here just lambda equal to 0. Not necessarily it's eigenvalue. So, but what I will get? I will get nothing else but lambda 1 multiplied by lambda 2 multiplied and so on multiplied by lambda n, right? Just from this expression. From the other point of view, what it will be, remember, it's determinant of a minus lambda, which is 0 multiplied on I. This is nothing else but determinant of a. So I got that, first of all, product of all eigenvalues is equal to determinant of a, but also if I have this a n lambda n, or not a, c n minus 1 lambda n minus 1 c1, sorry, c1 lambda plus c0, right? So it's polynomial, my polynomial, characteristic polynomial, right? So equals to 0. So this is my equation for lambdas, right? But then if I substitute here lambda equal to 0, so I'm getting that this coefficient is nothing else but determinant of a, right? So you know that in your characteristic polynomial, this coefficient, the free term, the constant, is always equal to determinant of your matrix A. Then, what we have found here, so we found that this coefficient c to the power n, so yeah, this c to the power n is always nothing else but negative 1 to the power n, where n is the size of your matrix, right? Okay, and this is always equal to sum of eigenvalues. Now, okay, let us compute this determinant using, for example, expansion along the first row. Then, okay, I use this like that, right? Or let me like that. This. Then, pay attention. When I'm computing the cofactor for this element, how many terms with lambda I will lose? Could you tell me? So have a look, like that and like that. So you see, for all other elements here, I'm losing at least 2 terms with lambda. So this and that. So one in my row, right? And one on the diagonal. So as a result, I know that if we are talking about, so all further cofactors will give me only powers lambda of powers of lambda n minus 2 and lower. So is it clear or not? Because I lost 2. So what is determinant? Determinant is product of the n terms, right? N entries from your matrix. But when I use this cofactor expansion, I see that I'm for all terms, further terms here, I'm losing 2 brackets with lambda, which means that they can produce at most lambda to the power n minus 2, not lambda to the power n minus 1. So what does it mean? It means that only term, so when I'm considering this, only term a11 minus lambda on the corresponding cofactor of this element, right? So these terms produce lambda n minus 2 and lower powers. But this term produce lambda n and lambda n minus 1 and all other powers. And if you will have a look, so how to get, so as we told already, so how to get lambda n minus 1. So you need, for example, to consider these multiplied on the corresponding cofactor. But then when you will be computing this cofactor, this determinant, so then you will get exactly the same situation here. So you need to multiply on that. So as a result, what you will get that the coefficient in front of lambda to the power negative lambda to the power n minus 1 will be nothing else but sum of the diagonal elements. This is called trace of a matrix A. So as a result, I'm getting that characteristic polynomial always looks like that: negative 1 to the power n lambda to the power n plus trace of A, or negative 1 to the power n minus 1 from here, lambda n minus 1 plus further terms, plus the last term is always determinant of A. But also from here we got that trace of A equals to, have a look, nothing else but sum of all eigenvalues. But I also have proven that determinant of A, this constant, is equal to nothing else but if you will substitute here lambda equal to 0, so all these will go away and it will be just product of eigenvalues. So why all this important? Because for 2 by 2 matrix, we have quadratic polynomial. So we are getting negative 1 squared lambda squared plus trace of A negative 1 to the first power lambda plus determinant of A equals to 0. Or in other words, lambda squared minus trace of A lambda plus determinant of A equals to 0. So for 2 by 2 matrix, you can just write your characteristic polynomial using this formula, and you will not make a mistake. So it's way easier. But also, please, when you're computing polynomials for 3 by 3, 4 by 4, just check that you got the right coefficients here, here, and here. Because otherwise you're making the mistakes and you don't know that you made a mistake when you're looking for characteristic polynomial.